feel like it's never any fun until you get to a word problem, right? So here is the big idea, the big picture here. You've got a baker that has all of these ingredients. That's all they have. And they know how much of each kind of ingredient they need for making a batch of cookies, for making a cake, and for making a pie. And we want to know how many of each kind of dessert can be made so that we completely use all ingredients on hand. Well, this comes down to defining your variables correctly and then writing your equations the right way. So what we don't know is how many of each kind of dessert is being made. So let's look at it this way. If we let x equal the batches of cookies, y is equal to the number of cakes, and z equals the number of pies. Okay, start nice and simple, right? Now, unfortunately, like we've seen in other word problems, there's nothing that tells us the total number of desserts that are being made. We just know about the ingredients. And it's the ingredients that have the limitations. And that's where we actually form our equations. So when we write our system, one is going to be based off of the eggs that are being used, one is going to be based off of the flour, and one is going to be based off of the sugar, because we know something about the total amount of eggs, the total grams of flour, the total grams of sugar. So pay attention to what we have here. So one batch of cookies uses one egg. So that means for the eggs, you'd have just one for the eggs. But it uses 60 grams of flour, so that means you'd have 60 grams times the number of batches of cookies, and 200 grams of sugar, so 200 times x. So that is a column that is specific to the ingredients for a cookie, or for a batch of cookies. Now let's look at the cakes. One cake uses 3 eggs, so that means plus 3y. So for every y cakes, multiply times 3, and that's the number of eggs. For flour, that's going to be 200 per cake. For sugar, that's 240 per cake. Now, please don't actually try to make any of these desserts using these ratios. It might taste incredibly gross. I was just creating a problem so that the numbers would work out nicely. Okay, good. A pie. A pie needs 2 eggs, so plus 2 eggs for every z pie. 150 grams of flour, so plus 150 for each pie. And then for sugar is 160 grams of sugar. Now for each of these, there is a total. The total number of eggs, 20. The total grams of flour, 1,370. The total grams of sugar, 1,840. There's your system. So we could just throw this into the calculator, but don't want to do that. I do, but I don't. Not for you, because I care about you. Let's turn this into an augmented matrix. So our augmented matrix would have 1, 3, 2, 20. Then we have 60, 200, 150, and 1,370. Then we have 200, 240, 160 for a total of 1,840. All right, so it's just like everything else. Again, we've got this process. We have this algorithm that we're going through. We want this to be a 1. We have that as a 1. We want to destroy everything below that, and so we're going to do that with row operations. Starting with doing negative 60 times row 1 plus row 2. And then we'll do negative 200 row 1 plus row 3 and replace row 3 with that. All right. Oh, that did not go right. All right, so the first row is still the same. Ooh, I'm getting loopy. All right, so negative 60 times 1 is negative 60 plus 60 is 0. Negative 60 times 3 is negative 180 plus 200 is 20. Negative 60 times 2 is negative 120 plus 150 is 30. Negative 60 times 20 is negative 1200 plus 1370 is positive 170. Now, negative 200 times 1 plus 200, 0. Negative 200 times 3 is negative 600 plus 240 is negative 360. Negative 200 times 2 is negative 400 plus 160 is a negative 240. And then negative 200 times 20 is negative 4,000 plus 1840 makes that negative 2,160. Okay. Now, I'm not happy with some of the numbers that I have here. I'm sure you guys are totally shocked at that. So here's what I'm going to do. I know that for this second row, I have to do row 2 divided by 20 and replace row 2 with that. For that last one, I don't want to have a negative there. And I also see that these guys have a common factor of 10, but also 12. So it's going to be 120. So I'm going to divide row 3 by negative 120 and put that into row 3. Oops. There we go. All right, so let's see if it makes the problem any easier. So divide the second row by 20. So that gives me 1. 30 divided by 20 is 3 halves. 170 divided by 20 is 17 halves. Fractions, you gotta love them, right? Now the last row I'm dividing by negative 120. So it's going to give me 0, 3, 2. And if I divide 216 by negative 120, just double check that that's 12 into 216. Whoops. That gives me 96. That gives me 18. All right. I can work with 18. All right. Now I need to get 0 there. So I've got to do negative row, nope. So negative 3 times row 2 plus row 3 and make that substitution. All right, so it's still going to be 0, 1, 3 halves, and 17 halves. 0, 0. Okay, so we got to do negative 3 times 3 halves plus 2, so that's negative 9 halves. That's going to be plus 4 halves, so that's going to make this negative 5 halves. And then we're going to do negative 3 times 17 halves plus 18. So it's going to be negative 51 over 2. 18, when I convert that into halves, would be 36 over 2. And that's negative 15 halves. Oh, what in the... Oof. I think that's where I was getting messed up. Why did no one tell me? Why am I using the braces when it should be matrix? I'm telling you. I think it's just one of those days. All right, but now we need to get this to be a 1. So we use the reciprocal. We're going to do negative 2/5 times row 3 and replace that with row 3. Again, with copying. And let me just erase this stuff over here. That's my scratch work. Goodbye. All right. And then this guy doesn't change. 17 halves, 0, 0. Multiply times the reciprocal of negative 2/5 gives me 1. And if I do 2 over 5 times 15 over 2, Those guys reduce. 15 over 5 is 3. All right. So we got 3. Okay, so at this point, we can use back substitution to get everything else. Okay. Or we could keep on going with this and do like the reduced row echelon form. So if I do negative 3 halves row 3 plus row 2 and replace row 2 with that, that's going to give me a 0 here. And then if I do negative 2 times row 3 plus row 1, that gives me a 0 up there. All right. So 1, 3, these guys are not changing. The other things are going to change. All right. So if I do negative 3 halves times 1 plus 3 halves, that's going to give me 0. That's what I meant to have. But now I've got to do negative 3 halves times 3 plus 17 halves. All right, so it's negative 9 halves plus 17 halves equals 8 over 2, which is 4. All right, so that's 4. And then I do negative 2 times 3, negative 6, plus 20 is 14, and that makes this guy 0 as well. All right, get rid of that scratch work. All right, the last thing I need to do is to get a 0 right here. So we'll do negative 3 times row 2 plus row 1 and replace row 1 with that. So at the end, we'll have this matrix right here. We have 3, we have 4. So the last part, negative 3 times row 2, negative 3, plus 3 is 0. Negative 3 times 4 is negative 12, plus 14 is 2. So we did all this to find out what x, y, and z were. But remember, x, y, and z were representing something real to us, right? So the question here is asking how many of each type of dessert should be made. All right, so from here, that means the baker should make two batches of cookies, 4 cakes, and 3 pies. Systems of equations to the rescue. We can take all that data, put it in this augmented matrix where we don't have to worry so much about x, y, z, and everything else. It's just pure numbers. And we do these row operations, multiplying and adding, and we get to our answer at the very end. And it's very clear what the answer is. And it's a process, it's a procedure, it's the algorithm. We do it, and we're done. So we get the answer, and then we make sure we take that answer and we interpret it so that we actually answer the question.